Right. So last time I gave you introduction to Postgres, and in our image cluster, if you go to this directory of the instructor, you can find the DDL statement inside the ddl.sql file, and this data.sql file has bunch of it's just so slow. Bunch of insert statement to populate some data in your database. But suppose you have really large data, and those data are stored in comma separated format like this, or white space separated file, and transforming this text file into a bunch of insert statements is going to be, boring and inefficient. So instead of translating each line into an independent insert statement, you can load this comma separated file or white space separated file inside the database using copy statement. But unfortunately, this copy statement shown in our lecture slide is for MySQL. I forgot to update this. So if you run this command, I believe it's going to fail in Postgres. So inside this sample DB directory, we have a Python script, and that generates bunch of data for this our university database. So you need to copy this Python file into your working directory and run it. Then you will get this subdirectory named university underscore data. And if you go there, lots of comma separated files. You can find lots of comma separated files. So let's look at one of these files. It's just so slow. Yeah. Oh, we have only 2 columns. Interesting. Let's look at student. Yeah, inside the student.csv, we have ID, instructor name, department name, and what is the last one? Maybe salary. And let's open this load Postgres.sql file. And then these first few lines will delete all records from the existing tables, and then we have a bunch of copy statements. And inside the Postgres, the copy statement needs to be escaped, and then table name will follow, and the following parenthesis is optional. I mean, if the comma separated file has attribute values exactly in the same order of attributes of the table, then you don't need this attribute named. And then we have this from keyword followed by comma separated file, and then the rest of the line indicates what format this text file is using. So we are using comma separated file. So we need to use this one. And what is null? I don't know. Oh yeah. So if the comma separated file doesn't have any value, if there's no character in specific space separated by comma, I mean, if you do not find any ASCII character between 2 commas, then that value will be treated as a null. That's the meaning of this second argument. So let's run this code. Open PSQL. Oops, sorry. I should. go to university data and run PSQL and type my own password, and then connect to my own database, and then run using \i command, and the SQL file location. Load postgres.sql. Oops. Oh. Maybe. Where am I? Oh, I'm in the same. I think this is the problem caused by this relative path and absolute path. Anyway, I'll fix this issue after the class. And after class, if you run it, then it's going to load a bunch of data in the sample database tables. Okay, let's go back to the lecture slide. So that is how you can create database schema and load data into those tables. Okay, now let's move on to chapter 3. Now you guys should be ready for DDL and DML. So SQL statements can be classified into two types of statements. One is called DDL, and this is about defining a schema. And when you define a table, you need to list attribute names and their types, and I believe I covered this slide last time. And each attribute should have a specific type, and these are the built-in predefined data types you can use in Postgres and Oracle and also MySQL. And the syntax of a create a table statement is shown in the next slide. So if you look at this example, create a table and table name, and inside the parentheses you list attribute names and their domain, their types, and they should be separated by these commas. And if you do not want null value for a specific attribute, you can put this non-null constraint after the data type. Then if you try to insert a record with a null value for name attribute, that insert statement is going to be rejected by DBMS. And in addition to this non-null constraint, you can specify some additional constraints like primary key, foreign key, and so on. And what is primary key? No one remember? ID that can uniquely identify a specific record of the table, right? And actually that definition is for candidate key, and primary key is a selected candidate key. So as a developer, you need to select one of those candidate keys, and once you select it, you can declare a set of these attributes will behave on ID of a record by putting this primary key constraint. Okay, what is foreign key? Foreign key means primary key of another table. So suppose you are you are creating a schema for instructor table. So instructor has ID, name, department name, and salary attribute. And here we have a department name attribute, and department name attribute, let's suppose department name attribute has been declared as the primary key of department table. Okay, so we are defining this instructor table, not the department table, but here inside the instructor table we have an attribute which is the primary key of another department table. Then you don't have to, but you can declare that this department name is a foreign key. This means that department name is the primary key of another department table. Okay. Why do we need this? whenever you try to insert a new record into this instructor table, because of this foreign key constraint, the DBMS will check the value you specified for department name attribute has been, the DBMS will check if the value you try to insert department name column exists in this department table. So suppose that currently department table has a computer science and electrical engineering, only two majors. And if you try to insert an instructor with department name bio, that insert statement is going to be rejected. Because this foreign key constraint enforces DBMS to check whether the user specified department name is a valid value that is currently stored in department table. Okay. And inside this instructor table, instructor's ID is the primary key. This is the only key that can uniquely identify specific instructor. So here we declared that primary key of this table is ID. Let's look at some more examples. Next, we define student table, student ID, name, department name, total credit, and again we have department name attribute, which is the primary key of department table. So we put this foreign key constraint. Student ID is the primary key of this table. And text table, this ID is student ID, and course ID is for course table, and section ID is for the section table. Do we have a course table? I'm not sure. Maybe we don't have only section. I think we have a course table, but it seems we are missing that foreign key here. Anyway, do we have it? Yeah, we have a course table, but somehow it seems we missed foreign key constraint for the course table. Anyway, we have a section table and section ID attribute inside the text table, and this is section ID and course ID and semester year. All these four attributes form a primary key of section table. Therefore, we put this foreign key constraint here. Why do we need these four attributes as the primary key? We are going to talk about it later. And this ID is for student. So here again we declare that the ID is the primary key of student table. And what is the primary key of the current text table? ID alone cannot uniquely identify a record because one student can take multiple courses. So ID alone is not sufficient. And what if we put course ID? What if we add additional attribute as the primary key? Still, it is not sufficient because a single course may have multiple sections, and a student may have taken multiple sections by retaking the same course in different semesters. So section ID alone is not sufficient to uniquely identify a particular record of this text table record. We need ID, student ID, course ID, section ID, semester, and year as well. We don't need the grade. A student cannot have multiple grades for the same text record. So grade alone, grade is not needed for primary key. That is why we have this primary key constraint below. Question? No. Each of these attributes is not a candidate key. We need all these 5 attributes as a single primary key. To uniquely identify a particular record, we need a student ID, and we need to know course ID, and we need to know section ID and semester and year as well. We need to know all these 5 attribute values, After that, we can identify a particular record. Okay. And in a table, there can be maximum just one single primary key. We cannot have two primary keys. There can be multiple candidate keys. Once you select it, there should be only one single primary key in any table. Next, course table. If you look at this second line, you see that primary key follows the data type. In the previous examples, we saw that we put this primary key constraint after the list of the attributes. But for simplicity, we can put this primary key keyword after the data type. It's just a matter of preferences. So you can put primary key constraint in the same line with the attribute definition, or you can put this primary key constraint after the list of the attributes. Okay, let's move on. So we just learned how to create a new table, and sometimes you may want to delete the schema of a particular table and then recreate it. In that case, you can use this drop table statement. Drop table student. This is going to delete the table definition from the DBMS. And if the table contains any data, all those data will be deleted as well. And here, optionally, you can put cascade keyword after this drop table statement. So when you have a foreign key constraint in another table, let's say student ID is declared as the foreign key of text table, then DBMS will think that this student table and text table, they are somehow connected. So one of the attributes in the text table is the primary key of student table. So when you have such a relationship, you cannot you cannot drop student table before you delete text table. So if you try to run drop table statement, in this case, DBMS will complain that one of the attributes of student table is being used as the foreign key of text table, so we cannot drop this table. And if you want to override that rejection, then you can put cascade option, then student table will be deleted. And the next statement is not DDL, but it is DML, but I just put this bullet here just to help you, just to avoid confusion. Delete from statement is DML, and this statement is going to delete all records from student table. So this is not related to database schema, but it is manipulating content of the table. Therefore, this statement is DML, not DDL. This drop table statement will delete the definition of a student table. So it is DDL, but delete only the content of the table, so it is DML. And sometimes you may want to add additional columns to existing table. In that case, you can run alter table statement. So R is the name of an existing table, and A is attribute name, and D is domain, data type, with some constraint. So if you run this statement, let's say currently table R has attribute XYZ, and when you run this statement, additional column A will be added to the schema. Let's assume that the table R previously contained some values, and now you just executed this alter table statement, then what do we need to do for these existing records? By default, their values will be set to null. And suppose you now want to delete this attribute G from existing schema, then you run the same alter table statement, but this time instead of add, you put drop keyword, and then attribute name like G will follow. Then the particular attribute will be deleted from the table definition. Question? So okay. Let me demonstrate. So after running the ddl.sql and data.sql, we have these tables in the database. And let's look at student table. It says that we have ID, name, and department name, and the foreign key. Here it says that department name is the foreign key which references department table. Okay. Now let's open and let's see the department table definition. And do we have foreign key constraint? Oh, still we have some foreign key constraint. Anyway, so student table is referencing department table, and let's try to run drop table statement here. Then if it succeeded, where is it? Oh, yeah. If we succeeded, then it is going to just say drop table output. But here we got some error messages saying that you cannot drop this table because another object, in this case, student table, is dependent on the definition of department table. Department table. Okay. And if you want to override it, you can put this cascade option, and if you put cascade option, then the department table will be also dropped together. All those dependencies will be considered, and those related tables will be dropped all together. Okay, that's it for DDL, and now let's talk about DML. DML is about reading and writing, and deleting, and update, upsert. Sometimes we call it upsert. Update, search, insert, delete. They are classified as DML statements. So this select statement is the most commonly used query. What it means is we access these tables. So we are selecting these attributes from these tables. And those selected attributes, selected records must satisfy a given predicate. Okay? So the condition, selection condition is specified in the where clause, and the table list is specified in the from clause, and projection operation is specified in the select clause. And the output of this select statement is going to be also a table. So this select clause corresponds to projection operation. So instructor table contains name, salary, department name. When you are not interested in all other attributes but name, you can run this select name statement. Then only name column will be retrieved. And one note here, one thing you need to note here is that SQL DBMS, all DBMSs are case insensitive. So only the values inside the parentheses, only those values specified inside double quote or single quote cares about cases, uppercase or lowercase, but all other SQL statements, all other keywords and table names, they are case insensitive. So this camel notation is no different from notation with all lower letters or all upper letters. They are equivalent. And last time when we learned the relational algebra, I told you that this is based on set. So any duplicates are eliminated and keep only one single unique record in the set. But SQL DBMS is a program, and DBMSs don't care about duplicate. And if you want to eliminate duplicate, then you need to use distinct option after the select statement, select clause. So if you put distinct here, any name will appear almost once in the output table. And if you want to keep all the duplicates, then you may put all keyword. So all performs the opposite. It is complete. It is the opposite of distinct option. But this is the default behavior, and therefore no need to put all option in select clause. Nope. Most of people don't use all option. Only when you want to eliminate any duplicates, then you can put distinct option. And suppose that a given table has really large number of attributes, and you want to select all the attributes. Then instead of listing each attribute name in select clause, you can put this wild character. Asterisk symbol denotes all attributes. And this select clause allows some simple arithmetic expressions like plus, minus, multiplier, division. Those simple calculations are allowed in select clause. So this query will retrieve ID of instructor, name of the instructor, and we have annual salary in salary column. But if you want to show monthly salary of each instructor, you can divide this annual salary by 12. This is going to give us monthly salary. This kind of arithmetic calculations are allowed. Now let's talk about predicate. So this where clause, the last clause in simple select statement, allows us to specify filter condition. And this predicate can combine multiple expressions using logical operators, and or not these operators can be used. And each expression must be Boolean. They should be either true or false. So let's look at an example query. This query scans all records in instructor table, and we check department name attribute, and if the department name is equal to computer science, and if its salary is greater than 80,000, then only when these two conditions are true, that record will be selected and included in the output table. That's the meaning of this select statement. Question? Okay. We learned the Cartesian product in relational algebra. In SQL, in query language, when you put comma in from clause, DBMS performs Cartesian product. So instructor teaches comma, this comma will be translated into Cartesian product. So we combine all records from instructor table with all records with teaches table. So let's say instructor had M records and teaches table has N records. Then the output table will contain M times N record. And the output table will mean nothing. It just populates all possible combinations of these records. That's what Cartesian product does. So it's not very useful in real-world application. But if you put where predicate with this Cartesian product, you can transform the Cartesian product into natural join operation. So instructor teaches, it's going to generate meaningless all possible combinations, and among the output, among all the records in the output table, you compare instructor's ID with the teacher's ID, and when they match, we select that record and show their name attribute and course ID attribute. So the meaning of this query is to find the names of instructors and course ID of those courses the instructors teach. Okay? Is it clear? Maybe before we move on, let me give you a simple demo. Let's select everything from instructor. Didn't I run it? Okay, inside the instructor table we have these instructors, and let's select everything from teaches. We have 15 records. Let's look at just possible combination. Srinivasan from computer science department has ID 10101, and we have these three teaching information. So that instructor named Srinivasan taught these three courses. Select everything from instructor, comma, teaches. This will perform Cartesian product, and it gives us a bunch of information. Srinivasan, this is from instructor table, and this is from teacher's table. And here we have another Srinivasan. So it seems the teacher's table has been used as the outer for loop, and instructor has been used as the inner for loop. So for this particular course, we list all the instructor information. Okay, that is what this query does. How many records do we get? We got 180 records in this Cartesian product. If you multiply 12 by 15, we will get that number, right? So let's make this query more meaningful. We want to match instructor's ID with teaches.id. By having this predicate, we get this information. Srinivasan taught these 3 courses. Okay, that's natural join operation. Right. Let's find the course ID, semester, year, and title of each course offered by Computer Science Department. And to write this query in SQL, you should know the database schema, and this is the schema that we use for this query. Course table has course ID, title, department name, and credit. Section table has these information. We want to find the course ID. Semester. Oh, semester is missing in course. Semester is in section table. Year is also in section table. Title of the course. Title is in the course table. And we have a filter condition. We only care about computer science courses. So department name should be checked. So some information exists in section, some information exists in course. Then we need to do natural join. You should think of natural join operation when we access multiple tables, and you need to find out what attribute should be used as the join condition. Here, course ID, and these 2 attributes are the only common attributes in 2 tables. So we will list these attributes in the select clause from section, comma, course, where section dot course ID equal course dot course ID, and don't forget about this filter condition. Department name must be equal to computer science. And every SQL statement must end with this semicolon. And here you need to check the first attribute in the select clause. We have 2 course IDs. Which one do we need to use? It doesn't matter. They will get the same value. In that case, you can omit the table name. But if they have different values, you must not skip the table name. But in this particular example, since we are enforcing both course IDs have the same value, it doesn't matter which table name we use for course ID. So in that case, we can avoid writing the table name. Okay. Natural join operation is so commonly used in relational DBMS, and therefore people came up with an operator for the natural join operation. So instead of having this where predicate, you can simply put natural join operator between the 2 table names. So instead of a comma, you may have natural join keyword. Then DBMS will perform natural join. And in this case, the common attributes will be compared, and only those records that have the same common attribute values will be retrieved. So that common attribute will not be duplicated in the output table. Okay. In the previous slide, when we do not use natural join, but this Cartesian product, course ID from section, course ID from course table will be included in the output table unless you specify projection attribute. But when you use natural join, the common attribute will be included only once in the output table. That's the only difference That's the only difference. And when you use natural join, the query becomes simpler and it looks more intuitive and easier to interpret. So we already saw this query. We are listing instructor's name and course IDs that they teach. So we perform the Cartesian product and we compare. We check this predicate for the join condition. And this query can be simplified by using natural join operator. However, when you use natural join, you have to be careful about common attribute names. An example is shown here. We have an instructor table and teachers table and course table, and let's focus on department name. We have instructor named Nam and another instructor named Alice. And Nam is from computer science, Alice is from electrical engineering, and 10 is for instructor Nam. Instructor Nam is teaching SW 3003, and he is also teaching 3021 in 25 and 2024. Okay, and you want to retrieve the course titles of the courses that instructor Nam taught. When you join instructor and teachers, we will get only course ID, not the course name. So if you look at the schema, the course title exists in course table. So it seems we need to join teachers table with the course table again. So we will join 3 tables in this example. And our intention is to compare instructor ID with teacher's ID. And we want to compare teacher's course ID with course's course ID. Okay? So our intention doesn't care about department name, but here we have department names as the common attribute. So when you run this given natural join query, you will get nothing. Why? So instructor natural join teaches will compare these 2 attributes. So Nam teaches SW 3003 and SW 3021, and Alice is teaching 3003 in fall 2024. Okay, that's the output of this natural join operation. Do I have? Give me 1 second. Oh yeah, I have. Oh, we are not going to. Suddenly, instructor name has been changed. Let's use this slide. So, after you perform this join operation, the output table will have 10 Nam and SWE 3003 and another 10 Nam and SWE 3021, and then 20 Alice SWE 3003, and some more attributes will be listed, and also department name will be listed. For Nam, it will be CS, another CS. For Alice, it will be electrical engineering. And this is the intermediate output table from this first natural join operation. And then we perform another natural join using course table. when you perform this natural join, we will compare the course ID from the two tables, and also we will compare the department name as well. Department name as well. SW3003 computer science, SW3003 computer science. Oh, we got one result. It says that Professor Nam is teaching database course that it will be retrieved. So it seems I was wrong when I said it returns nothing. So we will get one record, and for the next record we compare SW3021 and we check the department name as well. So we will get another record saying that instructor Nam taught multi-core computing. Okay, and then we check. And then let's check the third record, Alice. Alice is teaching SW3003, but she's from electrical engineering, and SW3003 is a computer science course. So because Alice is working in a different department, her information is going to be dropped. Okay. So although Alice taught database course, that information is not going to be shown in this select query. Okay.
The course is that name coming, so first this name doesn't include that.
Ah.
Then potential join is nothing more.
Typo. Thank you. Yeah, every year I fix some errors and try to improve it, but
There's also extra period, I believe, in the instructor training.
another typo. Thank you. And also this example doesn't match with the previous slide. Anyway, this is the message that I was trying to say here. So when you perform natural join operations blindly, unlike your, regardless of your intention, DBMS will find the common attribute names and use those attributes as join condition. Because of that, some records might be dropped. Okay. So a correct way of writing this query is this. It is okay to use natural join for instructor and teachers, but for the third course table, you need to do Cartesian product and explicitly specify the join condition. It says that we are not comparing department name for join operation. That's what this query means. Right. Next operation, rename. So in relational algebra, we used this row symbol, and in DBMS, we use edge operator. So an example is given here. When you have this kind of arithmetic expression in select clause, it is recommended to rename the attribute column. Attribute name. Why? Let me show. Select name salary. Oops. Divide by 12. From instructor. So in SQL prompt, it doesn't matter. You can put a single line, single query in multiple lines, or a single line. It doesn't matter. So the first column is named as the attribute name defined in the instructor table. But once you have this, since you have this arithmetic expression, DBMS doesn't know what's the name of this second column. when there's no arithmetic expression, the given attribute name will be used as the name of the attribute. But when you have that expression, it is recommended. It is recommended to rename like this, as just renamed the second column. Okay. Also, sometimes you can rename the table. You can rename the table using the same as operator. Why do we want to change the name of the table? For simple query, you don't need, but when you have very long query with lots of tables, repeating the same table names here and there will be, inconvenient. It's going to make the query very long. So sometimes you may want to shorten the table name. That is one reason. And also, sometimes you may want to use the same table for different purposes. Like, do you remember the grandparent relationship example that you saw in the last lecture? In that case, you need to change the name of the table to specify whether you are accessing this table for your grandparent relationship or child relationship. So, in that case, by renaming the table, you can avoid confusion. And in some DBMS like Oracle, as must be omitted. In Postgres, I believe, I haven't tried, but I believe you can use as operator, and you may not have as operator. Just put white space between the new name and old name, then this table name will be renamed to this alias. Let me try it. I haven't tried it in Postgres. Select t.name from instructor as t. Okay, it worked. And what if I omit as? Oh, still it works. Okay, so in Postgres you can have as operator, and you may omit as operator. Yep, still it works. So as is optional. Next, string operation. In where predicate, you can use equal symbol for string matching operator. And sometimes you may want to do pattern matching. Then you should use like operator, as shown here. So like operator is a pattern matching operator. Uh-oh. Our university need to upgrade it. So string matching operator, like, can use two wild characters. Percentage symbol matches any number of alphabet characters, and underscore matches just one single character. So consider this expression, percentage DAR percentage. This means any string that contains DAR as a substring. DAR can appear as the prefix, postfix, or in the middle. It doesn't matter, as long as this name attribute contains these three characters, then like operator will return true. Okay? And sometimes the value may have percentage symbol. So suppose you want to find some records whose attribute values contain 100% as the string. So in this case, percentage is not the wild character, but it is actual ASCII character. In the case, using escape character, you can escape it. And what character do you use can be specified. I mean, if you want to use pound symbol as the escape character, you can put pound symbol here, and you can put 100 pound percentage. Then this pound symbol will be treated as the escape character, and the following character will be treated as just normal, regular ASCII character, not the wild character. Some more examples, some more patterns. Intro percentage will match any string that begins with intro. And percentage comp percentage will match any string that contains comp in the middle or in the prefix or postfix. And underscore underscore underscore. Then this pattern will match exactly 3 characters. And underscore 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 percentage will match any string any string that has at least 3 characters. Okay, and there are some string manipulation operators that you can use in DBMS. This double pipe symbol indicates string concatenation. In modern high-level programming languages, we usually use plus symbol to concatenate 2 strings, but in DBMS we use this double pipe. And upper function, lower function will transform the ASCII characters into uppercase letters or lowercase letters. And length will return a number specifying the size of the string. And substring will extract substring from a given string. So this is the input string, and if a position is 0 and length is 3, then the first 3 characters will be returned. If a position is 2, length is 2, then 0, 1, 2. From the third character, third and fourth character will be retrieved from substring function. Next, order by. This is sorting. This performs sorting. So you are selecting instructor's name, and if you want to list those names in increasing order, you can put order by clause. And if you want to list those names in descending order, then you can put DESC option after the attribute name. And if you want to use multiple attributes as a sorting condition, then you can put comma and another attribute. So if there are instructors with the same name, then those instructors will be sorted by their department name. Okay? Lexicographic sorting can be done in DBMS. And this ASC is usually omitted because this is the default behavior. So usually we don't use ASC, and when you want to sort in decreasing order, you may use DESC. We have an example of lexicographic sorting. In this case, these 2 attributes are used to sort the output records. Next, range query. Suppose you want to find the instructors who make salary in this range. Any instructor making more than 90,000 but less than 100,000, then you may use AND operator, like salary greater than or equal to 90,000 and salary less than or equal to 100,000. This expression can be simplified with between and operator. So this is range operator. If salary is in between these two numbers, and it also include, if the salary exactly matches 90,000 or 100,000, still that is going to return true. So equal condition should be noted here. That is range query. And tuple comparison. In nowadays modern programming languages most support this kind of tuple assignment operation. Similarly, in DBMS we allow tuple comparison. So when you compare instructor's ID with teacher's ID, and when you check department name ID with this specific string, you can put two conditions using AND operator. Instead of using AND operator, you can list those multiple attributes inside parentheses and use a single equal operator. That's tuple comparison. Next, set operation. You can have multiple select queries, like select something and another select statement. Between these two select operators and select queries, you can put union or intercept operator, and each of these select statement will be executed, and then the output tables from these two queries will be unioned or intersected, or we will perform set difference operation for except. And they are set operators. Since they are set operators, by default duplicates are eliminated. But if you do not want to delete duplicates, you should use all option after those set operators. Question so far? No? Next. Set operation examples are listed here. This is the query that finds courses that were offered in fall 2024 or in spring 2025. So this first query selects courses offered in fall 2024. This selects courses offered in spring 2025, and union combines these two output tables, and intersect finds common record from the two tables, and except will delete these records selected by the second query from the output table of the first query. And in DBMS, some attributes may have null values, and to check whether a particular attribute value is null or not, we use isNull operator. You must not use equal operator. This is not allowed. You will get syntax error. IsNull together, IsNull, these two keywords together makes a single operation. And null value in DBMS has a special meaning. It means unknown value. So suppose you select salary plus 1,000 from instructor table. Let's suppose this query. And Alice, Bob, there are two instructors, and this guy is making 1,000, and this guy, the salary is not known. When you run this query, the output table will say Alice 2,000 because of this expression. And for the second record, this query will return Bob and null. This is not 0. This is unknown value. Bob may make some money, but just we do not know what. I mean, we just do not know how much he is making. So this is some value that we do not know. And even if we add 1,000, still we do not know the result, right? That's the meaning of null. So when you run this query, the second column for Bob will be also null. So the next slide describes how what values will be returned when we use null value in these logical operators or comparison operators. So what is this value? 5 less than null. Is it true? False? We do not know. Null can be smaller than 5. It can be greater than 5. We just do not know. So since we do not know, this comparison operator will return null value. And null not equal null. Is it true? They may have the same value. We just do not know. So the output is also null. Is null equal to null? No. Unknown value can be different from unknown value. So this is also null. We cannot say false. They may have the same values. So when you use comparison operator using null value, returns null value as well. What if we use null value for OR operator? So null value or true. Is it true? Yes. As long as one operand is true or returned true, so regardless of this null value is true or false, the output is true. If the other operand is false, the output depends on the unknown value, so we do not know what is the output. So null or false returned null. Okay? Following? Null or null? We do not know. They may both have null value, false values, or one of them may have true. We do not know, so it is unknown. For AND operator, even if one operand is true, the other operator must be true to return true value. But since we do not know what is the right operand, this is going to return null value. False and unknown, even if this unknown value is true, since the other operand is false, the output will be false. Unknown and unknown, we don't know. What about NOT operator? This negates the Boolean value of the operand. We do not know whether this unknown value is true or false, so even if we negate it, still we do not know. And so let's suppose we have a where predicate and expression 1, expression 2, expression 3, blah blah blah, and some of them are or and blah blah blah. While we are evaluating each expression, we consider these logics and return null values as the output for some operators, and for the next level operator we again null as we treat null as unknown value and generate the output for the next level operator, and blah blah blah. And at the end, finally we are going to have either true, false, or null value. And if this entire expression is evaluated as null value, then we treat it as false value. Okay. Question?
Professor, what's the motivation for this, like, to treat the null as unknown? Because it doesn't feel natural, because in most programming languages we get an error if we try to do any of those manipulations, right? But what was the motivation for the developers of DBMS to treat it differently than in other languages?
Motivation. I didn't develop DBMS in the beginning, so I do not know their motivation, but
What was the design reasoning for this feature?
That's a really good question that I have never thought about it. Well, I will check the history and let you know next time. Why? I think one possible reason, I'm not quite sure, but one possible reason is database tables can evolve. Like you can add new column into an existing table, and maybe we can initialize the new column using 0, but that may cause, that may cause some trouble. I don't know. So when you initialize a new column, maybe it is better to say that we will populate those values later, but at the moment we do not know their values. Yeah, but that is a really good question. I will check and let you know next time. Give me 1 second. We are almost done with basic DML, but since we are running out of time, maybe we will stop after aggregate function. This is so simple. So just like we can use arithmetic operators like plus, minus, multiplier, division, we can use these aggregate functions in select clause. So let me give you examples. So this query select only computer science instructors and calculate their average salary. Then this is going to return just one single Scala value, one single value, but still in the form of a table. Something like this. And the next query accesses teachers table and do some filter operation, and then it checks. It eliminates duplicate IDs and then count how many records we have in the output table. Again, the output table will have a single value, but still in the form of table. And if you are curious about how many records you have in a particular table, you can use this count function with asterisk operator. And this aggregate function is commonly used together with the group by operator, but I think this is going to take some time to explain this slide, so let's stop here. Any question? If not, then I will see you on Thursday.